Thank you. So it took me some time to come up with a title which is related to what I think should be the topic of the conference, but it's definitely not related to the title of the conference. But I think there is enough intersection. So this is, in some sense, offshoot of a very long project with Jim Collins and Karen Workman, which have been going on for, like, I don't know, 5-6 years. Okay, this project has like a lot of like geometric intuition and motivation. I'm practically going to skip all of it, and I'm not really going to get close to like what usually is like part of this project. Okay. So. Okay, now this is. Oh, okay. Okay. Okay, so what I'm going to talk about is essentially representations of out Fn, and what we did is we found like a nice, interesting construction of representations, which in some sense is like pretty generic. So I'm not really willing to conjecture it, but it seems to me that like all representations of out Fn actually arise from this construction in some way or another. Okay. So what is known? So there is like one relatively easy way to construct representation of automorphism group of the free group. So what you do is like you use the canonical map from out Fn onto GLNZ, where you just act on the homology or on the Billinization of the free group, and then you turn any GLN representation into a representation of out Fn. Okay, so that's relatively easy, and like you don't expect to be that powerful, but in some sense, if you think what's really going on, you can modify this construction a little bit, and you can get quite a lot of things. So what are the obvious ways to modify it? Of course, you can replace like homology with like some other like small quotient of the free group, like nilpotent groups of small class, and then do the same construction. This is going to replace GLNZ with some kind of like regroup, or at least a lattice in a regroup, which is going to have GLNZ on the top and some kind of like unipotent part on the bottom, and like you can more or less do the same construction. Another thing you can do is you can play with some finite index subgroups and like do induction and combine them, and essentially it seems that that's all. So this is some kind of like a very strange question, but like the question is like, can you really do anything else? Is there any representation which is like completely far from this picture and not related to this one?
Are you looking for finite dimensional representation?
I'm looking for finite dimensional. And in some sense, the answer is no. Like there is like actually nothing known, at least like nothing known to me. And part of this project was like we accidentally stumbled on something which was like turned out to be a representation of out Fn, and we thought that it's actually completely different from this one. And then we spent some time thinking on it and actually realized that it's the same. Or it's not exactly the same, but it's related. Okay, so here is like, what is the result? So if we start with any co-commutative Hopf algebra, and I'm going to explain what this thing means, then you can define an action of the automorphism group of Fn onto the n-tensor power of this Hopf algebra. If you want to have an action of the outer automorphism group, you can pass to a suitable quotient, which is like reasonably well defined, and we more or less understand it. Okay, so what's our motivation? This is where actually everything started. So Jim had some kind of project which was to understand like something about the Johnson-Cock kernel. So this is a map between some filtration which arises from mapping class group into some real algebra which has some combinatorial structure, but it's relatively messy. And what we did was like we were looking at like this map, and like you realize that there is an abstraction from this map being surjective, which you can express in some kind of like combinatorial language. And we realized that this combinatorial language looks like it's computing cohomology of some action of out Fn. And from there, like we more or less like went back and tried to extract what is the action, and like we essentially discovered this action, and then the theorem that like the abstraction is exactly the cohomology of this action is like essentially trivial. Like it just rephrases like how the action is defined and like the combinatorial structure behind everything. And I'm completely going to skip this part. Also, if you specialize your Hopf algebra in the correct way, you can actually recover everything I said before from this kind of picture in a relatively nice uniform way, and so on. Okay. That's not going to work. Is it going to work? Yeah. Okay, so let's start with the Hopf algebra. Okay, so Hopf algebra is something like a very nice and very rigid combinatorial object. What it is, it's a vector space with a bunch of maps. So there are many maps, and like it gets, the definition seems like very messy if you haven't seen it before. So what are the maps like you need to put there? You have a multiplication, so this is a map from H tensor H into H. I'm assuming that all maps are linear, so you can think of it, this really forces your multiplication to have a distributive flow and all these kind of nice things. You need to have something which is called a co-multiplication, which is essentially a dual to the multiplication, and it goes in the opposite direction. It goes from H into the H tensor H. You have a unit, which is like essentially element 1 in terms of multiplication. You have a co-unit, which is the opposite. And you have an extra map, which is called antipode, and I'm going to explain this thing in a moment. And these guys have to satisfy tons of axioms. And I'm not sure actually what is the minimal set of axioms for these guys, but I don't think you can get away with less than 10. What I'm going to show you is probably about 20 axioms, but I just want to put them in like useful way and don't want to just try to find a minimal set. Okay, what kind of axioms we're putting? For example, one of the axioms is that, like, as an algebra, so if you ignore the co-multiplication, the co-unit, and the antipode, this is just an algebra because you have multiplication into the unit. This thing has to be an associative algebra. So if you start with 3 copies of H, you can go to 1 copy of H using 2 different ways, and these guys have to commute. So you can write it in this way. But this is not really the best way to write it because, like, things are getting very messy, and if you start using this notation, things are going to completely get out of control. So what is a nice way to do this thing? Is to essentially start drawing pictures and represent everything using pictures. So what my pictures mean, I'm going to read everything from left to right. So here I have 2 copies of H, which I represent them by 2 strands, and I use the multiplication to combine them into 1. So that's how I think about the multiplication map. I have the co-multiplication map, which is the opposite. Unit and the co-unit, they're essentially creating a string and cutting it because, like, the field is like 0-dimensional object when I think of it as a 0 tensor power of H. Okay, so let's try to give an example what this thing means. So you start with 2 copies of H, and you end up with 2 copies of H. So you have a map from H tensor H into H tensor H. What do you do with this map? The first thing you do is you take each of these strings and you split it into 2 using the co-multiplication. So now at that point, you have 4 copies of H. So that's this map. You have the delta tensor delta, which means splitting this one and splitting this one. In the middle, what I do is I switch the second copy and the third copy. So this is this kind of thing. And, like, for me, this represents the canonical switch of the 2 factors in H tensor H. And then I combine the things using some multiplication. So I use 2 multiplications. Okay, so this picture, at least for me, is much nicer than this one. Okay, there is a lot of bad things going on. For example, I have to essentially reverse everything when I go from this language to this language. Because at least for me, the functions always act on the other side. But when I draw pictures, I prefer to read them from left to right. And, like, this causes, like, a bunch of confusion. But okay. Get used to it. I'm not going to use this language at all, so this language is, like, a little bit easier. Okay. Okay, so what are the axioms? There are, like, many, many axioms. As I said, the first axiom is the associativity of this thing as an algebra, which means that if you start with 3 copies of H and you go into 1 copy of H, you can have 2 different ways to do it, and they're the same. And, like, in some sense, graphically, they're represented by these things, which for me is much nicer than saying, like, that the composition of some tensors with multiplication and the identity is the same. You have the co-associativity, which is like the dual picture of this one. You reverse everything. Unit and the co-unit is essentially you create an empty thing and you multiply it, then you haven't done anything. And it doesn't matter whether you multiply on the left or on the right. Co-unit is the dual of this thing. There are a couple of extra axioms. Like the main axiom is that the multiplication and the co-multiplication are compatible, which means really this picture. So in some sense, like a Hopf algebra, you use the multiplication to have an algebra structure. You dualize everything, and the co-multiplication gives you a co-algebra structure, and these two structures have to commute. And like this is what this thing is saying. And there is one extra axiom, which or a bunch of extra axioms, which involve the antipode. Essentially, it says that the antipode is, in some sense, inverse to the identity in some algebra. Okay. And okay, you have to add a few more things. You have to add an extra stuff that the antipode behave nicely with respect to multiplication and the co-multiplication. And the thing you have to keep in track is that this creates an extra twist. So the antipode is not an algebra automorphism, it's an algebra anti-automorphism because it switched the order. And like the same thing for the co-algebra stuff and so on. Okay. What I'm going to care about, and I'm going to put one extra condition, is that my algebras are co-commutative. So commutativity means that if I do the twist and after that I do the multiplication, it's the same thing as just doing the multiplication. Co-commutativity is the dual of this thing. So if I do the co-multiplication and add a twist, I haven't done anything. And this is nice because it implies a bunch of extra things which are much easier. So for example, it implies that the antipode is of order 2. So I really can think of the antipode as some kind of like flip. Okay, that's annoying. Okay. Now, so what are the examples? Because like if you haven't seen Hopf algebras, then like nobody can actually digest this definition in like 2 minutes. That's so there are two main examples of like Hopf algebras, or like essentially co-commutative Hopf algebras. One of them is arising from Lie algebras. You take any Lie algebra, you can form the universal enveloping algebra, which is like in some sense like you just formally write a tensor algebra of the Lie algebra and impose like the obvious relation. So this has a nice algebra structure. You have a multiplication and a unit. They have to satisfy all the axioms. And in order to make it into Hopf algebra, I only need to define co-multiplication, the antipode, and the co-unit. And since I have like many compatibility conditions, what I really need to do is I really need to define these things on the generators, and they're going to be forced on everything else. So what is the co-multiplication on the generators? If I have an element from the Lie algebra, this is sent to H tensor 1 plus 1 tensor H. And of course, this is co-commutative because if I change the first and the second factor, like these things are going to get swapped. I have to define the antipode, which is like just -1 on the Lie algebra. Co-unit is just 0. Of course, you have to verify that like you can extend this thing to satisfy all the axioms. This is like something which is not that hard, but like it requires some checking, but not a big deal. Okay, what is the other example? The other example is like a group algebra. You start with any group. You take the group algebra. Again, you have a multiplication and a unit, so you need to define the co-multiplication and antipode and co-unit. You define them on the basis elements like this. So as you see, the antipode is in some sense the group inverse. The co-multiplication is something like stupid, like you're just doubling everything, and so on. And again, you have to check that all the axioms are satisfied, but not a big deal. What is the next thing you can do? In some sense, what you can do is you can combine these two things. So if you have a Lie algebra and a group of automorphisms of this Lie algebra, you can take these two and you can form something like a semi-direct product. As a space, this is actually a tensor product of these two spaces, but like you twist the multiplication so that like when you conjugate group elements, Lie algebra elements by the group elements, this comes from the action of G on, gamma on G.
Tensor product, G cross G, what is it?
It's a formal element in like the group algebra tensor the group algebra. So the group algebra has a basis consisting of group elements. When you tensor it, it has a basis consist of pair of elements. In fact, this is one of the base elements. So sometimes this thing is called some kind of Smosh product, and they use something else, but like this. And actually, this is a nice theorem saying that like, if you stick to characteristic 0, that's everything you can do. There is no other examples of co-commutative Hopf algebras. Of course, if you drop the condition that things are co-commutative, you have like tons of examples which are like quite hard, and like there is practically no chance that you can classify them. Okay. Okay, I did. So now let's go to the action. Okay, that's annoying. Okay, so how we discover this action? As I said, like we have some kind of like combinatorial object which computes something which we want to understand, and we thought that like this combinatorial object should be represented as like should compute the cohomology of some action. So what you need, like we have a model for like a space of the group. So like we have a bunch of simplices, and like if you want to compute the cohomology, then like you have to have a vector space where the basis consists of like a simplex tensor, like an element from the module. You have some kind of boundary maps, like which like you can more or less track down, and you want to compute like the homology of this complex. And like if you don't know what is the action, the only thing you see is like this kind of combinatorial structure. So what happens is like more or less you see what the module should be, and using the boundary maps, you can see how some elements from the group have to act on this thing. And then you see, okay, let's see whether this thing is a module, and let's see what kind of stuff is going on. So what turns out is that you see some of the generators of out Fn, and there are three types of generators which are like actually appearing in this picture. You have a permutations which like just move the generators around. You have inversions which like take a generator to its inverse, and there is a transvection which like takes one generator and multiplies by another one. So you have to keep track how this thing acts. And the first two things are obvious. Like you have permutations which have to act on H tensor n. There is only one thing you can do if you want to hope that it's natural. You just have to permute the factors. There you don't really have any choice. For the inverse, it's the same thing. Like you have the antipode, which is like a canonical element of order 2, and like you use it as like to correspond to the group inverse. So really, the only thing you have to define is how the transvection acts. And like when you go to this kind of messy combinatorics, what you extract from it is that you have this picture. So I can think of the transvection as automorphism of the free group on two elements, which sends like x1, x2 to x1, x2, comma x2. And how it's supposed to act? You take H tensor H, you use the co-multiplication in the second factor, and then you combine this thing with the multiplication in the first factor, and that's it. Okay, so you can hope that this is an action. But the problem is, really, this is the worst possible way to define an action of a group on something. Because you're defining on the generators, you have to check that everything is consistent. So the first thing you need to do is you have to find a presentation of the automorphism of the free group. Okay, such things are known, like they're not that complicated, but still it requires some checking. The nice thing is that at least there are presentations of the automorphism of the free group, which consist of like a presentation of the symmetric group, or even like the sign symmetric groups, which is actually built into this picture, so we don't have to check it. And there are only 3 or 4 extra relations which you have to deal with it.
But it's easy to check if you just act on the free group itself. There's a universal H, which is the group ring of the free group, and then you see it topologically.
No, you cannot really do it like that. Okay, the proof actually comes into this thing, but I don't think you have that the universal Hopf algebra is the same as the group of the group algebra of the free group. I'm not sure that this thing. So, for example, how do you get n generators out of the Hopf algebra? Why do you have n not like 2n or 5n? You have to do some work. It's not completely abstract nonsense. But okay, if you start to look at it from the correct viewpoint, it's completely trivial. and in some sense you're correct. Okay, so you have to check a bunch of relations, and so for example, one of the things you have to check is this one. Okay, so if you chop it here, this should represent the automorphism of out of Fn, which is out of F2, which is for the tree. I never remember what is it. I think it sends x1 to x2 inverse and x2 to something like x1, x2 inverse or something like that. And like you directly check that it's for tree in out Fn, it should act as this thing because like it's a product of generators. You have to do this thing and you have to check this one. And okay, I said, well, this should be checked. And Jim sent me this thing. Okay. So this is his proof that like this thing is satisfied. You know, some kind of like standard game with like playing with diagrams and so on. But you know, this is not really the best proof. Like when you start to draw these pictures, you can follow them, but like you have to draw like 4 more things which you have to verify, and it gets a little bit messy. So I was very unhappy with this kind of like way to define action of out Fn. So I was trying to figure out like, can we do it a little bit better? And I realized that there is much better way to do it, and like I think that's exactly what Rand tried to suggest. What you are doing is the following: you take an automorphism of the free group, and you can think of it as like it sends a generator to a bunch of words, and like you count how many times each letter appears in all these words. So what you do is you take your elements in h to the n. Each element corresponds to the group to the generator of the group. First, you apply the co-multiplication many times so that you can split it so that like each element appears enough times so that like it corresponds to the number of xi's which appears in this words w. You use the antipode to flip the corresponding factors, which corresponds to the inverse. You permute them and then you multiply. And which is actually what exactly happens with like the definition of the transvection. I just have x1 and x2. I have 2 x2s in the image, so I have to use the co-multiplication to split x2 into 2 and then follow it. So in some sense, like this is like equivalent definition. But using this definition, it's very easy to check that like this is consistent. So it's like essentially the only thing you have to check is that you have some freedom how to choose these words W. Like, okay, you don't have freedom if they're reduced, but like you have to make sure that like if you pick a non-reduced word which corresponds to the same thing, you're not going to change anything. So that's the only verification which you have to do is like if you add xi inverse somewhere, it's not going to change the picture, and that's much easier to verify. And actually, what it follows is that you're having an action not of the automorphism group of the free group, you're actually, you have an action of the semi-group, which is the endomorphism group of the free group. Because in this picture, I don't really care that this thing is invertible. I can just define it in any way, and all the compositions are going to be satisfied. Okay, so again, this is something which I was not extremely happy, because you still need to do some checking. And eventually, I figured out that there is a very nice definition, which actually I really like, and it goes into help you understand what's going on, which is a way to express everything without checking anything. So the only thing you have to do is like you have to define the corresponding space in the correct way. So what I'm going to do is I'm going to start with 2 Hopf algebras, and I'm going to define some space of homomorphisms between them. And I'm going to think of this as a natural transformation between some functors. So let me try to explain what are the things which appear. So there are 3 categories which are going to come up here. One is the category which essentially like determines all the Hopf algebras. So this is a category where objects are integers and morphisms are given by the pictures which I was drawing all the time. So the morphisms are generated by multiplication, co-multiplication, unit, co-unit, whatever else you have. They have to satisfy all the axioms, which are like, I had them before. But really, this is the category where you have all the pictures, nothing else. One thing you have to notice is that like this is not just a category, this is a tensor category, because you have a natural tensor product. You just put 2 pictures together, everything goes through. Okay, what is another category you can do? You can start with a vector space, And you can take a category NV, which is like just the objects are the vector spaces V tensor 0, V tensor 1, V tensor squared, and so on. And the morphisms are all the linear transformations between these two spaces. So this is like a subcategory of the category of all the vector spaces. And now what is a functor from the first category to the second one? Okay, this is really giving a Hopf algebra structure on the vector space, because the only thing you need to do is like you need to define where the multiplication is sent to and where the co-multiplication is sent to. And like if you keep track of what it is, like multiplication is going to send to some linear transformation from V tensor V into V. And the axioms have to be built into this picture. Okay, so really like you have these canonical functors which are representing the Hopf algebra structure. And what you can do is like you can look at the natural transformation between these two functors. And okay, if you don't like to think about natural transformations, you can take an equivalent definition. Okay, what is a natural transformation between two functors? This is a corresponding map between the objects which satisfy a bunch of compatibility conditions coming from the morphisms. So you can think of it as a sequence of maps from h1 to the power n into h2 to the power n, and they have to satisfy about 10 compatibility conditions, which like you can list them down. I really don't want to because they're messy. But there is one thing which is important and I really want to stress, is that these categories, they have a tensor structure. All these functors which appear here, they are monoreal functors and they preserve the tensor structure. So when you talk about natural transformations, you have a choice whether you have to keep this tensor structure into account or you can ignore it. If you keep the tensor structure into account, you're going to get morphisms between Hopf algebras, which is not, okay, which is something interesting, but it's not a vector space, so it's probably not going to give me the stuff I want. So I really want to make sure that I ignore the tensor structure. So I don't impose the condition that the map F, if I take the maps Fi and Fj, if I put them together, I'm going to get the map Fi plus Fj. This condition is not there, but everything else is there. Okay, so this is like very natural definition, and from there you can actually do a lot of things. Okay, so for example, if I replace one of the Hopf algebras with a group algebra of any group, then I have a natural action of the automorphism group of the group on this thing, because it acts on the first Hopf algebra, and therefore it acts on any set which is naturally constructed from this Hopf algebra, like this set of natural transformations and so on. So in this picture, the only thing you have to do is to prove the following lemma. If you start with the free group, the set of these natural transformations can be identified with h to the n, and the identification is like the trivial one. You have this kind of sequence of compatibility functions, and you send all this sequence to, you evaluate the end function on the generating set. That's it. You don't do anything else. Okay, so here you need to actually do some work. In order to prove this thing, you need to actually go into definition, into what are these compatibility conditions, and check that like this actually going to determine everything using like the axioms, and like you can go back in all possible ways.
Can you explain again what the map is?
Okay, so these natural transformations, you have a bunch of linear transformations from h1 tensor I into h2 tensor I. And they have to satisfy many compatibility conditions, which I don't bother to write them down. But essentially, they're coming from the fact that, like, say, you apply the co-multiplication in the first factor. So this gives you a map from h1 tensor n into h1 tensor n plus 1. You have the same thing on the target, and then you have a map. Okay, probably I can write it down like this. Can we do it? No, I think that's fine.
Yeah.
I don't really want. So you have Fi from h1 to the I into h2 to the I. So what you can do is you have hi to the I. You can use the co-multiplication in the first factor, I minus 1, so h1 to the I plus 1. So you can map it with fi into h2 tensor I. You can use the same co-multiplication.
Martin, I'm not sure that everybody here in the room can see the board. Can everybody see the board?
Okay, so
I'm actually asking. Can everybody see the board?
Would anyone like to see the board who can't see the board?
do you want me to move it? Okay.
If nobody complains, we can get
Okay. Okay, I think I'm going to go on if people are not complaining. So there are many stuff which like you have to do, but essentially what you do is like you have one thing here, you compose it with something which is built from the Hopf algebra structure. You have the corresponding thing on the other side, and the f have to be compatible. That's the only condition you have. So this identification is you have this kind of sequence of functions fi which goes between these tensor powers. And you completely ignore most of them except one, which is the nth one. So this is a map from the n tensor power of the group algebra into the n tensor power of h. You just evaluate at one particular point, which is the generators. So maybe I have to write this thing not like x1, x2, xn. Maybe I have to write it as x1 tensor x2 up to tensor xn. So that's how I define this thing. So when you keep track of everything, what happens is that the action of out fn is exactly the same on h to the n. It's exactly this action when you push it to this identification. Okay, so did I answer your question or? Okay. And actually, some part of this lemma is pretty general. So for example, if I replace the free group with any n-generated group, I can get exactly the same map, but it's not going to be surjective anymore. So I can identify this space with a subspace of h to the n, but like it's not everything because you have to satisfy some relations which are coming from the group gamma, which you can express them as some linear conditions here. But they're a little bit messy to express, at least in this language. Okay, you have to do a couple of examples and see it. Okay, so how I'm doing? Okay, I have 10 more minutes. So 10 more minutes is enough to go over a few examples and like actually tell you that this thing is reasonably interesting. Okay. Okay, as I said, co-commutative Hopf algebras, they're essentially coming in two flavors. You can have something which comes from groups, you can have something which comes from real algebras, you can combine them and get something else, but like that's essentially everything. So now let's see what's going on when you start playing with groups. Okay, so start with any group. Take the group algebra, which is the Hopf algebra. What is the h to the n? H to the n has a basis which consists of n tuples from group elements. And now what is the action? The action of out fn is nothing else but like you send one n tuple to another n tuple, which corresponds to the canonical action of out fn onto g to the n. And this is really, you can think of g to the n as homomorphisms from the free group into the group G, and you act by automorphisms there. So here you're not recovering anything. You're taking the standard permutation action of out fn on some nice set, and like you just linearize it. That's it. Not a big deal. Okay, so where things start to get interesting is what happens when you start with real algebras. So if you have a real algebra, you take the universe of enveloping algebra, and so this is more or less the same thing as the symmetric algebra of G, at least as a vector space. Okay, so actually the same as the co-algebra, but like whatever. Now, what happens when you take n copies of this thing? Taking n copies of a symmetric algebra is the same thing as taking a symmetric algebra not on one copy of G, but on n copies of G. So you can identify h to the n with a symmetric algebra of G tensor n-dimensional space. Okay, so this immediately gives you an action of gon k on this set, because you can use gon to act on k to the n. You can push this thing to a symmetric algebra, and after that you can combine this thing with the map from out fn into the gon. And at first we said, okay, we're very happy. We essentially recovered the standard action. You can use this thing to compute cohomology and whatever. And then we realized that this is not the same action. What we're getting is completely different action than the standard one. So of course, like if the algebra is abelian, everything is going to coincide, but in general, they're not going to be the same. But they're in some sense connected. The reason is that you shouldn't think of U of G as the symmetric algebra. The inverse invariant algebra has some kind of nice filtration, and you then look at the quotients. The quotient becomes like symmetric power, so the symmetric algebra is not U of G, but is the associated gradient of this thing. So this action you're getting is you're taking the action, the previously defined action of out fn on UG to the n, you take the grading and you pass to the associated gradient action. So the action we're defining is a little bit more because it has more information and like it has some kind of higher order terms which like what you get down there. So in some sense like this is nice, in some sense it's bad. It's bad because like we wanted to compute the cohomology of this action. When you have this thing, like you have no idea how to compute cohomology because like this kind of stuff is going to mess up the action a lot. Yeah.
So you're saying that I acts trivially for all these examples? Do I understand correctly?
That's the first example.
Yeah.
And that's why I said the actions do not coincide.
Does not coincide
with the previously defined action. Okay. So in the previously defined action, the inner automorphisms do not act trivially. That's why they are different.
The inner or the IA?
Anything.
Are they interacting?
Yeah, the inner is acting.
What?
The inner acts in a non-trivial way.
By what?
by conjugation?
By some form of conjugation, very fancy form of conjugation. It's, okay, I can write it down, but it's not going to give you, okay.
Because there is a famous conjecture that they actually always by a solvable group, usually solvable group of the inner, and this is a counterexample.
No, this is not a counterexample. Okay, so, let me explain this thing. First, this is not a finite dimensional representation, because U of G is excuse me?
At the beginning, you told us that your representation will be finite.
I'm going to make it finite dimensional in a second. Right now, it's not a finite dimensional because U of G is not a finite dimensional vector space. However, U of G is filtered by a finite dimensional vector spaces, so you have an increasing sequence of subspaces, and these things are preserved by the action. So you can chop it off and look at like lower degree terms, terms of degree up to something, and this is going to become a finite dimensional space. And you can act on this thing. Now, when you act on this one, this thing has a filtration, and the inner automorphism, and not only the inner automorphism, everything which acts trivial on the organization is going to push you down inside this filtration. So what's going to happen is that the inner automorphisms are going to act in some nilpotent way, always, because they're going to push you down. So, okay, in this case, like this conjecture is trivially verified. You don't have to work on, okay, you have to say something, but okay, so in some sense, like there is much better way to view this picture and to understand what this action is. So you can think of the Hopf algebra, U of G, as essentially the algebra of distribution on the regroup. You just exponentiate the algebra, you get the regroup. Okay, I'm assuming that the algebra is finite dimensional, the regroup is compact because I just want to be lazy. Now you look at like functions on the group, you just localize at the identity and you dualize. And that's what's going to give you the Hopf algebra. So you can think of the Hopf algebra as some kind of like dual to the algebra of functions in some way. Now, n times the power of the Hopf algebra is going to be dual to the algebra of functions not on G, but on G tensor n. Now on G times n. Now on G times n, you have an action of automorphism group. And now the action here is like the dual of this action, so if you trace everything. So in some sense, like you're taking the action of out fn on n tuples, and like you do some very fancy form of linearization or like small perturbation and see what's going on. Okay, yeah, so that's exactly what I said. Like this is really the action is just induced by the action on this thing. One thing you can do, and I'm still trying to understand how much stuff you can do from there, is you can replace the free group with some other n-generated group. Then the corresponding thing here is not going to be h to the n, but it's going to be essentially the dual to the algebra function on the representation variety, or at least like the representation variety close to the identity. So this gives you like a very nice algebraic way to study the representation variety, and you might be able to get like information about the singularity near the identity using this kind of stuff. And okay, the stuff which I really want to do, and okay, I believe that it's doable in some sense, is to take this picture and try to form some kind of deformations. So you can deform this thing and this thing to make them into non-commutative Hopf algebras, and then this is going to give you some deformation of the representation variety. And if you do it correctly, you should be able to get like a bunch of like strange representations, like something related to quantum representations of mapping class groups out of this thing, if you just fix the deformations in the correct way. Okay, so let's do one last example in the last minute or two. Okay, so let's start with a finite group. Let's start with a representation of this group. I'm going to assume that it's irreducible, but you don't really care about this thing. And I can view this thing as a trivial Lie algebra with a zero multiplication. So now I can form the Hopf algebra, which is I take the inverse numerical algebra of this trivial module M, which is just saying symmetric algebra. I take a semi-direct product with a group algebra of the finite group, and this is something. Okay, again, this is like very far from being finite dimensional, and I cannot really do anything, but what I can do is the following. I can fix a homomorphism from the free group into G. Okay. Okay, so now I have an action of the full automorphism group of the free group on h to the n. However, h to the n is built out of several pieces. I have a piece which corresponds to the finite group and piece corresponding to the Lie algebra. So when I take the n tensor power, I'm going to have like stuff coming from the Lie algebra, and in front of it, I'm going to modify it by an element and tuple of elements in the group. When I act by the automorphism group, I'm going to permute the factor corresponding to the action of out of n onto the group, onto the n tuples of the group, and then I'm going to do something in the Lie algebra. But I can go and restrict myself to a subgroup of finite index which corresponds to the automorphisms which fixes phi. And then I'm going to get an action of this subgroup only on the n tensor power of the Lie algebra. So what I'm going to get is I'm going to get a subgroup of out of n, a finite index, which is going to act on this thing. So this thing has a nice filtration by the degree, so I can chop it off at any stage I want, and I'm going to get a bunch of finite dimensional representations. So I can chop it at the first stage. So when I chop it at the first stage, I'm going to induce an action on the n tensor n on the direct sum of n copies of m, because this is the linear part here. I just have m in one of the pieces. Okay, so if you put some standard assumptions that like m is irreducible, phi is surjective, and a bunch of other stuff, then what you can see is that here this m to the n has an invariant submodule which is isomorphic to m to the n minus 1. Essentially, the quotient corresponds to some kind of inner automorphisms which are like inner conjugation by m. So when you do this thing, you're going to get an action of finite index subgroup of out of n into m to the n minus 1. So this is exactly the action which like Rx and Fritz discovered like almost 10 years ago, using the taking the kernel of phi, acting on the organization, decomposing into a bunch of stuff, and getting a bunch of things. Okay, probably it's not exactly the same. Maybe there is some kind of small duality. You have to replace m with the dual module in order to get them exactly the same. But the way you get this representation you immediately get this thing into a very nice algebraic group, because if you keep track of everything, this action is defined in terms of the action of G. So the action is like, you just permute the copies of M and you hit them by suitable elements in the finite group. So in some sense, this action is always inside the double centralizer of the action of G. So it commutes with like the ring of coefficients, and like it immediately wants you in some kind of like nice arithmetic group, and you don't have to check anything about compatibility.
What's the sense again?
So this construction immediately gives you that this sends you inside SLN of the corresponding ring of integers.
Inside,
not onto. It's not always onto. You know that it's not onto. In order to make it onto, you have to make an additional assumption that this morphism is redundant. You have an extra one free generator to do it.
No, we don't know that this is a necessary condition.
Well, you have an example saying that like it's not surjective when it's redundant. Okay. But, okay, what I'm saying is like, okay, you have to do some work. Okay, it's not that much work in order to say that like you get the representation into the arithmetic group.
But you are not claiming that by doing it this way, like the difficult part is to really to show that the image is a full arithmetic group. I mean, can you?
I can do it.
Perspective, can you get another way to see it?
It's more or less the same proof. It boils down to the same proof. If you have one redundant generator, what you get is you start playing with forced derivatives and you get a bunch of like enough unipotent matrices which generate the group. But like it's the same proof. There is nothing I can do to simplify it. And that's how actually I can prove that the representations are the same. I just go into the generators and express everything in terms of forced derivatives, like how they act, and like I just see that the formulas are the same. Okay, so okay, I really don't have very nice applications of this thing. I'm just saying that like this is a really nice uniform way to build a bunch of representations, and like you can get tons of stuff out of it. Okay, you cannot really get anything really new because like you don't have that many co-commutative Hopf algebras, but like you can put everything together in some reasonable way. I suppose you can get some interesting stuff if you look at like the action not on the first degree part, but say on the quadratic terms or something. Okay, like of course it's going to be graded, so the action on the quadratic part is going to be essentially the square of this action, but it's going to, you might have a non-trivial extension between these two modules, which are going to give you something. But somehow I'm not really in the mood of like doing like heavy cohomology and trying to understand extensions and like to measure stuff inside this thing. Okay, I think that's enough. Maybe I'm even running out of time, so.
Thank you, Martin. Questions? Okay. If not, we thank Martin again and all the speakers from the morning.